Okay, so let's work through this worksheet here, which has some limit problems, various types that we've been looking at, but a lot of work on limits of infinity and limits at infinity. All right, so in 1a here, okay, the limit as x approaches infinity, 2 plus x squared over x cubed minus 1. All right, so because I'm going to infinity, that's usually the type where I'm trying to compare the numerator and denominator. And so immediately I notice that we've got an x squared on top and an x cubed on the bottom. So the bottom is certainly dominating. So I could simply say this is 0. All right, because the x cubed from the bottom going to infinity is going to dominate over the x squared on the top going to infinity, and this whole fraction is going to go to 0. All right, in this one here, we have the limit going to infinity of 2 plus x squared over x squared minus 1. So very similar to the one above, except instead of x cubed on the bottom, we have x squared on the bottom. Okay, so we actually have the same power on top and bottom. So what we'd be doing is we'd be looking to look at the coefficients. And so we essentially have a 1 there over 1 there. We get 1 over 1, or 1, because we had them balancing out. Okay, limit as t goes to infinity of 2 minus t plus sine t over t plus cosine t. All right, so because it's a little more complicated, let me go back to the dividing by the highest power in the denominator of a power term. And so let me divide through by t and see what happens. All right, so I get 2 over t minus 1 plus sine t over t all over 1 plus cosine t over t. So that's when I divide everything by t. Now let's take a look at everything. As t goes to infinity, 2 over t will go to 0. Then I have, minus 1. Then I have sine t over t. Remember, sine t over t as t goes to infinity, it's going to go to 0. Then I have 1 in the denominator. And then another 0, because just like sine t over t, cosine t over t is going to go to 0 as t goes to infinity. So I get negative 1 over 1. I get negative 1. Okay. So in D here, okay, limit as x goes to 0 now. So I always have to be very careful looking at what the limit is going to. Sine 5x over sine 4x. All right, it doesn't look like there's a lot I can do here because this is going to be a 0 over 0, but then I remember that special limit. And so basically, if I do an interesting manipulation here, so let me put sine 5x over there, and then put sine 4x in the bottom over here. All right, so if I can create these special limits in a way where I don't really change the problem. Okay, so usually I can't put in variables on their own, but because I actually need an x here and an x there to go along with the sine terms. And so I can put in x over x. All right, so then the other idea is I need, for this sine 4x and this sine 5x, I need the correct constants along with them. So I would need a 4 on top to go along with the 4x in the bottom. But in order to do that, I'm going to have to also put a 4 in the denominator to balance it out. And if I want to put a 5 down there with the sine 5x, I would have to put a 5 there. Okay, so then all we're going to do is basically take the limit of each one of these terms. But as x goes to 0, that's a special limit, sine kx over kx, and goes to 1. Kx over sine kx, that's a special limit, that goes to 1. And this is a constant, goes to 5/4. So in the end, I get 5/4. Okay. How about the limit as x approaches negative 2 from the left of x plus 3 over absolute value of x plus 2 over x plus 2? Okay. So the thing that makes me pause here is the absolute value. But realize we're only going to negative 2 from the left. So I have to take a look and think about what the absolute value of x plus 2 is. Well, the absolute value of x plus 2 is one of two things. It's either x plus 2 or it's minus x plus 2. It's x plus 2 when x is greater than or equal to minus 2, and it's minus x minus 2 when x is less than 2. That's just coming off of the basic idea of what absolute value means. All right, so because I'm going to negative 2 from the left, that means that I'm actually less than negative 2. So this is the case that I'm only concerned about here. All right, so that means that I could actually replace the absolute value of x plus 2 by a minus x plus 2. Okay, and now I notice the x plus 2's can cancel, and I actually end up with limit as x approaches negative 2 from the left of negative x plus 3. And now I'm down to a simple plug-in. I'm going to get negative, and then plugging in negative 2 plus 3, I get 1, so I'll get negative 1 overall. Okay, so the part that we're coming from the left here had to actually do with that absolute value part. Okay, limit as x approaches 0 from the left of x squared minus 2 over x. Okay, well, as x approaches 0, x squared is definitely going to go to 0. But then I have minus, and this x, 2 over x, so this x is going to 0 from the left. So this whole 2 over x term is actually going to an infinity, but because it's a positive 2 over negative tiny numbers, it's going to be negative infinity. But essentially now I have this answer being 0 minus the negative infinity, so I actually get positive infinity. All right, next one. X goes to 1 from the right. Well, let's just figure it out. X goes to 1. 2 plus x goes to 3. 1 minus x goes, so from the right to 1, so slightly bigger than 1, so 1.1-ish. So these are going to end up going to 0, but in a negative manner. So I've got constant over 0, a non-zero constant over 0. It's a type of infinity. I've got a positive, and negative. So overall negative. So negative infinity there. Okay, find any vertical asymptotes. So vertical asymptotes, we've seen that they're either built in, or they're a place where the denominator is 0 and the numerator is not. So in this first one here, it's pretty obvious to me that the denominator would be 0 at 2. All right, so I've got a vertical asymptote at x equals 2. In the second one, I have to be a little careful. If I factor this, I get 2 minus 3 over t times t minus 3. So the denominator is 0 when t is 0 and 3, but the 3, oops, I shouldn't actually cancel it out because this is the function here. But I have to notice that a canceling factor like that is a 0 over a 0. We've seen this before. That actually ends up being a hole in the graph. And in fact, the only vertical asymptote is from the t equals 0. So if you have a canceling factor there, That's a hole in the graph. All right. ln x plus 3. Well, we know that ln has a vertical asymptote at x equals 0. And if I know that ln of x plus 3 just backs this thing up three spaces, then I know that actually, that's not a great ln graph, but we'll take it, that now the vertical asymptote has moved from x equals 0 back to x equals -3.